Okay, I'm Amir Hossein Mirza Bozorg, and in this webinar, I want to talk about how to resolve Abacus explicit errors like excessive distortion or wave speed. About the videos which I upload in my YouTube channel, you can ask your questions and don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. I'm reading this for people who watch this video when I upload it in my YouTube channel. And also you can ask your questions when I finish my presentation. We will try to answer all questions regarding the video details in the comments below, and new Abacus users who want to develop their modeling skills faster in their projects can request user-oriented online and offline services. Subsequently, we offer step-by-step guidance, tutoring, and consultancy regarding their problems. The only service, the online service includes online sessions, and the offline service includes creating special tutorials. In addition, a combination of the two can be requested. And 50% discount codes are announced on our Abacus Telegram channel and official LinkedIn page. Their links are provided in the description below the tutorial. As you know, every video in the YouTube has a description below it, and I write a lot of useful information about our videos in the descriptions. And this is the table of content of this webinar, and we will talk about a lot of useful things, and finally you will have a deep insight about the explicit solver. Okay, first of all, I want to talk about the 50% discount code, which is Black Friday 2023, and you can use it for buying every premium Abacus tutorial and package from November 18th to 24th. But this is for people who don't participate in the webinar. For you that are participating in the webinar, we have special offers, and I will tell you later on at the end of the webinar. Okay, this is only for people who don't participate, but for you who are participating, this will change. Okay, 50% will change and some other things. I will tell you later on. And also, when it is uploaded, I will put the link of the 50% discount code video here. I will put it here and everybody can reach it. Let me accept others. Okay. Some of the Abacus errors are common among all the Abacus solvers, including errors related to the material definition or mesh quality. Also, each of the Abacus solvers has its errors. Resolving each Abacus solver's error needs knowledge about the solver itself and how it works. In this webinar, several common errors of the Abacus explicit solver will be discussed in detail, and solutions will be suggested to resolve each of them. As you know, Abacus has two structural solvers for solving mechanical and structural problems. The first one is the Abacus standard solver, and the second one is the Abacus explicit solver. Abacus standard solver uses implicit integration techniques for solving linear and nonlinear problems, and Abacus explicit solver uses explicit integration techniques for sorry, I forgot to sorry, I forgot to share the screen with you. No, is it shared? Yes. I'm so sorry. Thank you so much for your message. Here is the, let me show you this again. And I told you the conditions will change for you later on, and also it was the first slide. And in the step module, when you when you want to create a new step, you if I open Abacus here for your better understanding, I create an arbitrary part, okay, an arbitrary part, and I import it to the assembly module, and now we go to the step. Here I click on create step, and you must select between these steps if you want to do a nonlinear analysis, because the procedure type is general. And when you select the dynamic explicit step, it means that you want to solve your problem with Abacus explicit solver. And I click on continue. And here I want to talk about some of these settings. Okay, I want to talk about some of these settings. Dynamic explicit is one of the available steps of Abacus explicit solver. Originally, it was developed for simulating linear and nonlinear dynamic problems. For example, it is suitable for analyzing low and high velocity impact, explosion, shock, wave propagation simulation, and other dynamic problems. By using some tools and physical concepts, you can use this step for simulation of static and quasi-static problems, such as some of the metal forming processes, quasi-static tests like 3 and 4 point bending tests, and tensile tests. Here in the incrementation tab, we have two options. Okay, the incrementation type can be set to automatic or fixed. And if you select the fixed method, you must determine the size of the time increment for Abacus. Here, I set it to fixed, and here I set it to user-defined time increment. Okay, for example, here you can enter 10 to the power of minus 5. Okay, you can set it to 10 to the power of minus 5. And this number will not change during the analysis. But if you set it to the automatic, if you set the type to automatic, the solver itself determines the time increment size, and it can change during the analysis. And we usually set it to automatic. Okay, most of the time we set it to automatic, but in some special problems we set it to fixed. Okay, one of these cases is the wave propagation simulation. Here I have a paper for it. It is for the simulation of lamp waves using the explicit solver, and actually it is related to the NDT field or NDI field, non-destructive testing or non-destructive inspection, that we put a defect in the structure and then use and then generate pressure waves and then these waves go to the structure and impinge the defect and goes back. Okay, they reflect, and then we can use sensors to capture this effect, and then according to the reflected waves, we can understand the position of the defect and its size. For example, this is the NDI or NDT. And from now on, I'm talking about the automatic method, because most of the time you must use the automatic method, and I will tell you why. And when you set it to automatic, the equation of determination of the time increment size when using the automatic method is this. The time increment size delta t must be smaller or equal to the minimum of LE divided by CD for all elements in the model. It is for all the deformable elements actually, because the rigid elements they don't deform, and this is for applied for all the deformable elements in the model. And LE is the characteristic length of element, and it is a function of element dimensions. For example, let me create some slides. For example, if your element is cubic, okay, this is a cubic element. LC or LE, it has several names. It is equal to this formula. For example, this is A, this is B, and this is C. Okay? For a cubic element, LC is calculated from this formula, and Abacus calculate LC or LE for all the elements, all the deformable elements in the model. And each element type has its own formula. And also CD is the speed of sound or the speed of mechanical wave in the material, and it is calculated from this formula. E is the Young's modulus, and rho is the density. For calculating the global time increment size, Abaqus Explicit will search the whole model, and the smallest calculated time increment size will be chosen. I want to mention that the explicit integration scheme is conditionally stable, but as you know, the implicit integration scheme is unconditionally stable. The stability condition depends on the time increment size. If you use the automatic type incrementation, the calculations are always stable because the algorithm always chooses a time increment size below the stability limit. But if you use the fixed type of incrementation, I mean this. If you use this setting, if you use the fixed type of incrementation, your chosen time increment size must always be less than the stability limit. If during the simulation the current stability limit goes below the chosen time increment size, the simulation is not stable anymore and it must be terminated. It means that For example, we have a delta t, okay, I mean delta t user, okay. For example, it is 10 to the power of minus 7 seconds. And during the simulation, delta tc goes, for example, to 8 multiplied by 10 to the power of minus 8. And here you can see that delta tc is less than delta t user, okay? And this is wrong. This is wrong. And after this point, the results are not correct anymore, okay? It must be terminated. But Abacus does not terminate it if you are using fixed time incrementation, okay? So, for example, for wave propagation analysis, you must use a value that you are sure about it, okay? You are sure about it. And also, in some simulations, the time increment size, the stable time increment size or critical time increment size, it decreases. Okay, it decreases during the simulation, and I will show you the slides related to it. Here, you can see a job monitor dialog box related to the explicit simulation. And the increment column here, number of solved increments are written. And in the total time column, the total resolve time from simulation onset is written. And in the CPU time, the elapsed time or computational cost from the start of the simulation in seconds are written. For example, it means that after 30 seconds, 0.07 seconds from the simulation time is calculated or simulated, okay? It is the real simulation time, okay? The CPU time. And in this column, the time increment size is written. Here, you can see that even it is increasing, okay? In some cases, it increases during the simulation. And in some cases, decrease and increase simultaneously. Since the time increment size is usually less than 10 to the power of minus 6, therefore the simulation needs a large number of increments. Here you can see that a large number of increments are solved. But when you are using Abacus standard solver, you can see that here we have 1, 2, 3, 4, 5, or maximum 1000, 2000. Okay, but here you can see that even for solving 0.07 seconds, 163,000 increments are solved. Why? Because we are using a small time increment size, okay? Because the solver is using a small time increment size. And according to these two equations, we can obtain some understandings. First, the bigger the dimensions of elements, the greater the time increment size. The element with the minimum stable time increment size will restrict the global time increment size. Here, you can see that if I increase LE or LC, both of them are correct. LE or LC, if I increase it, then delta T increases. And the bigger the amount of Young's modulus, the smaller the time increment size. Here you can see that if we increase E, then CD increases. If CD increases, delta T decreases. And the bigger the amount of density, the bigger the time increment size. Here, if I increase density, CD decreases, and when CD decreases, delta T increases. And this is the idea for using mass scale. Okay, this is the idea for using mass scaling. Then I want to talk about ALE, or arbitrary Lagrangian Eulerian technique. The adaptive meshing technique in Abacus combines the feature of pure Lagrangian analysis and pure Eulerian analysis. The type of adaptive meshing is often referred to as arbitrary Lagrangian Eulerian analysis. The Abacus documentation often refers to ALE adaptive meshing simply as adaptive meshing. ALE adaptive meshing is a tool that makes it possible to maintain a high quality mesh throughout an analysis, even when large deformation or loss of material occurs. By allowing the mesh to move independently of the material, we can do the simulation, and ALE adaptive meshing does not alter the topology. Topology means elements and connectivity of them. The topology of the mesh, which implies some limitations on the ability of this method to maintain a high quality mesh upon extreme deformations. Here I want to explain the ALE with a simple example. Here we have a column and we apply compressive load to it. If we only use the Lagrangian method, which is the conventional or traditional method, most of the time you use the Lagrangian method. Then here we have severe distorted elements. But when we apply ALE to this model, because of the remeshing of the domain, then here we will not have any distorted element. And you can see that the quality of the elements are maintained. This is a good example for the comparison of using ALE or not using ALE. In this case, I have applied ALE to the model. This is the simulation of an extrusion process. Cold extrusion or hot extrusion, there is no difference between them. For both of them, it's better to use ALE method. Here you can see that by applying the ALE method, even during the simulation, the quality of the elements are maintained. But in this case, that ALE is not used, you can see that elements near the contacting face are distorted. Here you can see that their shape is changed. It's because of the friction. It's because of the friction forces and related tractions that makes this deformation. But by applying ALE, it is resolved. Okay, it is resolved. And even you can see that the difference in the stress contours, and here you can ask me that which one is more accurate. Okay, which one is more accurate? This one, this stress field, or this stress field? Basically, this one is more accurate because here you can see that the elements are not distorted, and ALE prevents elements from having severe distortions, and it's very important for resolving some of the Abacus errors. Okay, I will talk about it later on. And so this one is more accurate than this one. And here we have a forge simulation, and in this case I have used the dynamic explicit step with implementation of ALE, and you can see that elements have a good quality even at the end of the simulation. And in this case, I have used the dynamic explicit step without implementation of ALE. Okay, without implementation of ALE. And here you can see bad distorted elements. Okay, you can see the bad distorted elements or severe distorted elements. And also in this case, I have used the dynamic implicit step, and also here we have severe distorted elements. Basically, in the metal forming processes that the workpiece undergoes large volumetric strains, we must use the ALE method. And if you want to define ALE, in the step module, you must go to the other ALE adaptive mesh domain, edit, and you must select the step that you want to use ALE. Here, for example, I define this dynamic explicit step, okay? And I go to other ALE adaptive mesh domain, edit, step 1. And I set it to use the ALE adaptive mesh domain below, and I select the region, okay? There is no need to select the whole model, okay? For example, if you want to apply ALE to a part of it, you can make partitions and then apply ALE to that region only, okay? There is no need to select the whole geometry. And then you must set frequency and remeshing sweeps per increments. Now I want to talk about these two parameters. First, frequency. In this case, I have set it to 5. It means that every 5 increments we have a remeshing increment, okay? It means that 5th, 10th, 15th, and 20th, and some other increments will be remeshing increments. And by increasing this number, the simulation time will decrease, and maybe the excessive distortion error occurs. And about remeshing sweeps per increment, here I have set it to 3. It means that in each remeshing increment, the selected region will be meshed 3 times, okay? It will be meshed 3 times. And by increasing this value, the simulation time will increase and the quality of the distorted elements will be improved more. Actually, there is no rule for determining the appropriate values for frequency and remeshing sweeps per increment for each simulation, okay? For example, for the extrusion simulation, for what I did here, okay, for this case, 5 and 3 are good values, okay? I have found them by trial and error. But, for example, let me show you another problem. Here we have an axis symmetric simulation. This is the deformable target, and this is the rigid projectile, and it impacts the target with a high velocity. This is a high velocity impact, and I have defined ALE for this part of the target. And if you see here, here we have a uniform mesh, but here I have defined an unmapped mesh because this region is not important for us. Only this region is important. And also, in the step module, I have used these settings. Here, the frequency is set to 1, and remeshing sweeps per increment is set to 60. Okay, 60. It means that in every increment, we must do remeshing and 60 times, okay? For every increment, 60 remeshing operations, okay? Um, also, uh, um, basically, this model is related to um, this free video from my YouTube channel, and you can watch it after the webinar, and I have explained a lot of things in this free tutorial. Okay, so from now on, I want to talk about the errors, okay? Uh, this webinar is related to Abacus explicit errors, and here I want to cover several important errors. The first one is this: adaptive meshing is not supported for fully integrated elements. It means that if you want to use ALE in your model, you must only use reduced integration elements, okay? For example, in the 3D domain, if you want to use hexahedral elements, you must use C3D8R, okay? For example, here, I click on OK, and if I want to mesh this part, I can only use this type of element if I want to define ALE, okay? If I use a full integration element or I use incompatible mode element, I cannot use ALE. Only with this setting, I can use ALE, C3D8R. And also, for example, in this model, if you see, also for this region, it is a reduced integration element, okay? It is reduced integration element. Also, for the axis symmetric explicit analysis, we don't have any other choice, okay? We don't have option for full integration, okay? We only have option, we can only use reduced, and also you can apply ALE. The next error, which is one of the most important errors of explicit solver, is the element contained in this set have distorted excessively. This error happens when some of the elements undergo severe distortion, and so this error happens. For example, in this simulation, if I go to the job module, here you can see this error. And in this error, sorry, where is the... Okay, for example, and if you see, Abacus talks about a set, okay? Abacus talks about a set. And in this set, the severe distorted element is added. So I go to the results to check for this set. Here you can see that if I use more colors, we have this simulation. the rigid projectile impacts the deformable target. And deformation happens. Also here you can see the damage contour, the damage parameter contour, and this is the JCC RT contour. This is the damage initiation parameter, okay? And SDEG is the damage propagation parameter. And here you can see that we have a problem. Okay, we have problem. And I want to show you the severe distorted element in the set. If you use the create display group option and you set it to elements, you can see the mentioned set. And here we have that element. If I go to the start of the simulation, we have this element, and then it deforms. Here you can see that ALE is applied and the topology of the elements is not changed. Okay, the topology is not changed. I am tracking the element. Okay, I am tracking the element, and what happens for it? Here you can see that element deletion happens. And finally, it is highly distorted. And I resolved it by changing the settings of the ALE. And in that video in my YouTube channel, I have talked about it. And you can go and check it. So we can find the severe distorted element. And I want to talk about the solution for resolving this error. First, you can conduct mesh refinement or generate elements with higher quality in highly deformed or highly distorted regions. The second one is implementing ALE, for example, in the bulk forming analyzes like extrusion, ECAP, and forge. Also, you can define damage behavior to remove highly distorted elements. In such cases, the defined damage behavior must be able to remove damaged elements. Let me go to property module, mechanical. For example, damage for ductile metals. Here I have worked with ductile damage, Johnson-Cook damage, and shear damage. Okay, until now I have not worked with these ones, but I have a lot of experience in using these three important damage behaviors, and all of them have element deletion capability. But for example, if you use hashing damage for composites, and if you use continuum shell elements for meshing your composite, then hashing damage model will not have element removal capability. But if you use hashing damage model for conventional shell elements instead of continuum shell elements, then hashing damage model has the element removal option. And for example, if you use the concrete damage plasticity model for modeling concrete or some kinds of soil, then in the newer versions of Abacus, the element deletion capability is added to this damage model. But in older versions, for example, 6.14, 6.16, 6.17, I think, in these older versions, this damage model does not include element removal. But in newer versions, for example, 2020, 2021 and 2022, uh, damage how to define element removal is added, element removal capability is added to this damage model. And also if you want to add it, you must define keywords. You must define keywords from here. Edit keywords. And but it is not related exactly to this webinar. And the last one is changing the element type from C3D8R to C3D8. Because as you know, C3D8R element suffers from the hourglass problem. And if you change the element types to C3D8, which is the full integration element, then this issue is resolved, but you cannot use ALE anymore, because if you want to use ALE, you must set the element type to C3D8R. And the next error is the ratio of deformation speed to wave speed exceeds 1. And in a physical and realistic simulation, the deformation speed must always be less than the mechanical wave speed. The mechanical wave speed is, I have talked about it previously. For example, in a solid part, when you apply a sudden force, an instantaneous force to a part, then mechanical waves propagate in a spherical form, okay, in a spherical form. And the wave speed is approximately equal to E divided by rho, which I have talked about it in the previous slides, if you remember. And this is the speed of sound. And if the deformation speed exceeds this value, then you will face this error. And actually, in a realistic and physical simulation, this must not happen. The deformation speed must not exceed this speed. So if this happens, Abacus will terminate the simulation because it is not physical anymore. And for resolving this error, you can use all the solutions suggested for excessive distortion error. Also, you can use a mapped mesh in the stress concentration regions, including contacting regions and loading regions. For example, in the simulation of high velocity impact, in the target, in the contacting region, if you see, I have defined a mapped mesh. But in other regions, okay, but in other regions, I have defined unmapped mesh because they are not important for us. Okay, only this central region is important for us. And this is the example, the second example of chapter 11 of my comprehensive Abacus package. And if I show you this example, here you can see that I have used mapped mesh here. And if I go to the job module, um, the best view. And here you can see that in the contacting region, I have used small elements and also mapped mesh. And both the target and element removal is defined for both the target and impactor. Okay. The last error is the zero element time increment estimate. If you see in this simulation, the stable time increment size is decreasing during the simulation, and finally it reaches a very small value, and then we have this error. Due to the excessive distortion of some of the elements, the stable time increment size decreases during the simulation until it reaches to small values. Procedures suggested for resolving excessive distortion error can also be used for this error. So you can see that when element distortion happens, several kinds of error can be you can face several kinds of errors. For example, this error or this error or this error. Okay, all of them can happen due to the excessive distortion or severe distortion. And finally, I want to talk about the discount code again. In my YouTube channel, here you can see you can watch this video about how to use the discount code. And for you, I mean for the participants of the webinar, as I mentioned before, we have special offers. The Black Friday 2023 discount code is valid for you. It is only for you, not people who watch this video after I upload it. For people who didn't participate in the webinar, they can watch this video and they can do according to it. But for you, discount code is valid up to 28th of November instead of 24th of November to receive a 70% discount instead of 50% discount on one or two premium tutorials of my YouTube channel, or one or two extended premium package of my YouTube channel, and for one or two chapters from the comprehensive Abacus package. But the code applies to the entire comprehensive Abacus package with a 50% discount code. It's like the others. And here is the preview of the comprehensive Abacus package. You can watch it. It has several sub-packages, and for example, sub-package for mechanical engineers, sub-package for structure engineers, and some other sub-packages. And also you can buy each chapter separately, and each chapter has its own preview. And also please read the descriptions. And if you see, some of our tutorials have a premium label, and some of them have free label. Okay, some of the free videos have extended premium packages, and I have talked about the packages in the description below each video. And also premium ones, they also have some explanations in the description. And that's it. And you can contact me using Telegram or WhatsApp, or send email to me. And from now on, you can ask your questions. If you have any questions, I will be glad to answer them. Yes, please ask your questions.
Thank you, Mr. Mirza, for this nice presentation. I have a question regarding the ALE adaptive mesh.
Yes.
I can remember in the previous webinar that was related to the Abaqus standard errors.
Yes.
You didn't talk about the ALE adaptive meshing.
Yes.
Is there any specific reason that it's just
Yes,
it's just
yes.
usable for this type of solver?
I
Or
will. Thank you. I know what is your question. Let me answer your question in. If my laptop works. Actually, we have. Here it is. Actually, we have three kinds of remeshing. Okay, ALE is one of those. Okay, ALE. Here, my in the you can reach the documentation via Google. It is the for version 6.14. It is in Google, and here in the Abacus analysis users guide. You can see that there is a good explanation about all the, if it is updated, yes. Basically, ALE is only included in the explicit solver, okay? But we have three kinds of remeshing. ALE is one of them. There are two other remeshing rules also, and I think the other one that is included in the Abacus standard solver is a I think it is named map-to-map solution or something like that. If I solution based, I have read about it previously here. Mesh to mesh solution, sorry. Mesh to mesh solution mapping, adaptive remeshing, ALE adaptive meshing. Okay, we have three kinds of remeshings in Abacus. For Abacus standard, you can use this, and also I think this one, but this one doesn't work for severe distortion. For resolving severe distortion, this one is used mesh to mesh solution. Okay, but I have not used it before. For explicit analysis, you can use ALE adaptive meshing. And that's it. Is there any other question?
Thank you.
You are welcome. Until the end of the this session, we have only 5 minutes. If you have any questions, please ask. I will be glad to answer your questions about Abacus. If you have any questions. Seper, sorry, Sina, don't you have any questions?
No, everything was clear.
Thank you so much. And basically, in the simulations related to civil engineering, most of the time we don't face any errors if you use explicit solver. But for mechanical engineers, this is not correct. And most of the time when they use explicit solver, they encounter these errors. But if a civil engineer wants to model the impact, for example, impact of a bullet to the concrete, to the reinforced concrete or something like that, you will face these errors. Or if you want to model complex, if you want to model a complex structure which undergoes some seismic or seismic loads, seismic deformations, then maybe you face this issue and such issues, and or when you define moving loads, for complex structures, for example, um, for example, a train passes, okay, from the railway, and here you have a kind of a structure, and you want to analyze the effect of crossing of the train on the structure, okay? In some cases, if your mesh is not appropriate, or if you have not defined damping correctly, then you will face these issues. But most of the time, mechanical engineers and aerospace engineers and material engineers, they face these errors, not civil engineers, and this is good for civil engineers. Actually, civil engineers most of the time, they face too many attempt error or time increment error, and so on. I think we have only 2 minutes. Yes, please.
So could you please confirm me, as I understood, in the same scenario, when we come up with the problems that face with high nonlinearity, or we have the severe distortion,
yes,
if we can do the simulation both in dynamic implicit and dynamic explicit, it's better to use dynamic explicit. Am I right?
Not always. The answer of this question is highly case dependent, okay? But yes, in some cases, for example, for metal formings, for all the metal forming processes, yes. For all the metal forming processes, yes. It's better to use explicit solver because it has ALE, okay? It has ALE. But for some other cases, for additive manufacturing, for example, no. For additive manufacturing, no. And for additive manufacturing, maybe this one, mesh-to-mesh solution works, okay? Maybe. But unfortunately, I have not used it. But it's also for managing severe distortions. Yes. And is there any other question?
Thank you.
You are welcome. 1 minute only we have, and thank you so much for participating in the webinar. And as I told you, you have these offers, and you can contact me via Telegram, WhatsApp, or email. Thank you so much for your participation.